The project's purpose is to design and fabricate a diagnostic system for low-temperature plasma generated by General Atomics' Surprise ion source. The diagnostic system will be measuring spatially and temporally the plasma's electron and ion density as well as the electron temperature. The team has developed a silicon wafer probe array to draw current from the plasma and a measurement circuit to filter interfering radio frequencies from the current measurements. Additionally, a Faraday shield has been manufactured to prevent eroding of some of the structural components of the system.
The measurement circuit PCB conditions plasma probe signals using a low-pass LC filter to suppress RF noise, followed by a resistive stage to convert current to voltage. A differential op-amp improves signal integrity by stepping down voltage levels. Multiple channels are implemented per board and routed through a multiplexer to the LabJack T8 data acquisition, controlled via Python scripts for plot visualization. DC power is converted and stepped down from 5 volts to dual-based plus minus 2.5 volts as a power source to the multiplexer.
To begin electrical testing, we will begin by testing the differential mux by applying varying input voltages and select signals, and verifying that the output correctly reflects the selected input across multiple test cases. Next, we will verify the cutoff frequency. To do so, varying sine waves will be applied at the input starting in the kilohertz range and increasing into the megahertz range to identify the -3 decibel attenuation point, which should be around 6.8 megahertz.
Faraday shield is integral in running the surprise test stand at higher powers due to the phenomenon of ion bombardment along the quartz vessel. The RF coil that generates the plasma through inductive magnetic fields also creates an electric field that accelerates free plasma ions towards the quartz. The ion bombardment erodes away at the quartz, adding impurities to the plasma. The Faraday shield reduces these capacitive effects while consequently lowering the magnetic field penetration from the coil. The goal of this project is to analytically find a design that balances these trade-offs. Optimization was performed largely through electromagnetic simulation in ANSYS. The design is being verified through physical testing within the surprise test stand. A thermocouple is placed into a groove along the outside of the Faraday shield, measuring its temperature while plasma charts are being fired. In addition, an infrared camera measures the temperature of the quartz vessel to ensure there is minimal ion bombardment eroding it.
To test the plasma eater probe array, cyclic voltammetry and electrochemical impedance spectroscopy are used to evaluate its electrical response. The setup uses 3 electrodes: the probe array as the working electrode, a reference electrode for stable voltage, and a titanium mesh counter electrode to complete the circuit. Cyclic voltammetry is used to verify electrical connectivity between the bump pads and probe pins, while impedance testing evaluates frequency response and signal stability, ensuring reliable measurements before plasma testing.
D3D is developing a new plasma source that utilizes radio frequency coupling, currently being tested using the surprise test stand. This project enhances the test system through the addition of real-time plasma diagnostics and a Faraday shield, reducing reliance on filament-based sources while enabling more reliable, high-power operation. Findings from the test stand are used to optimize tokamak performance, enhancing plasma control, reducing maintenance limitations, and enabling more consistent high-power performance.